I'm in Benguerir. I'm in Benguerir, a small city between Marrakesh and Casa, and Rabat, just for you to figure out. And since January 2022, I'm the director of the Accelerated Research Center for Metallurgy, as you may know, because still making processes must change in order to reduce their CO2 emission. And now new strategy to make a new steel for automotive application are mainly driven also using hydrogen. So my department is mainly devoted on energy storage application, polymer composite, and also circular economy in general. What are the motivation of studying gas solubility in materials, I would say? Is first to get a fundamental insight in order to get, for example, the possibility to determine Henry law constants, which can then provide the possibility to calculate solvation properties in order to have information at the microscopic scale. However, as you may know, research are now also focused to develop and design new application. And particularly now, when we look at the real demand on energy and also the real demand on reduction of pollution. And our goals will be mainly in future to develop a new hydrogen, which we can call black, which is from coal gasification, gray from fossil fuel, green from hydrolysis, from seawater, for example, and using renewable power, blue from natural gas with carbon capture technology, purple from methane pyrolysis techniques, purple from nuclear power, and white is from hydrogen naturally occurring in nature. The other side from this hydrogen technology is a real need to develop new carbon capture strategy, not only carbon capture and sequestration, but also to move to carbon capture and utilization. And many of the work focus on many universities are based on carbon capture utilization to capture chemically, I would say, the CO2, and then to reduce, then to form a new C1 molecule, which is the main goal to and route for the chemical to formulate then liquid fuel, for example, to develop new fertilizer. That's the motivation of our group and the motivation of this talk today. How, from fundamental point of view, we can assess data and how fundamental data can lead and drive application. That's a good question. And if I ask a question to the audience, do you think that engineers really care about the accuracy of the data from gas solubility perspective? I don't know, please speak. Again, it's a workshop, and the workshop I have to change it. And as Ala probably mentioned, and we already discussed about a lot of point of uncertainty and how to determine it. But the first thing is, from thermodynamic point of view, we need to understand from the fundamental point to develop fundamental knowledge to answer directly industrial partner, for example. But how fundamental data can lead application? That's also a good question for, especially for students to answer. Then motivation from this talk will be to determine gas solubility in technological material. And during this conference, you had the chance to learn a lot of property surrounding ionic liquid technology. And I started my young career in 2002 within ionic liquid. So it's something like 20 years of study on ionic liquid, and specifically on thermodynamics and gas solubility. And recently, I also start to investigate gas solubility in porous material, mainly thanks to solid-state isotherm measurements, thanks to porosimeter or BAT techniques. And then, more recently, in literature, and I will show some example, communities start to look at porous liquids. I will define porous liquid later on. Of course, solubility data are measured by using different experimental devices. Some of them are built by researchers, some of them are available commercially. And commercial equipment, pieces of equipment must be really used with a great care, because at some point we do not control, for example, gradient of temperature, which may occur within the system and so on, which may affect the quality of the data without speaking any more on uncertainty. Data treatment and recommendation are very complex for normal liquid, I would say. A lot of work has been done. I will discuss a little bit on this later on. But the question is, can we select systems which are recommended data for such complex system, including ionic liquid, porous material, and porous liquid? That's a good question. And we will try to understand within this talk if it's possible or not. Just because I didn't know that the audience would be based on very high-level scientists, I just put some historical papers first. And the first paper that I had a chance to read was published by William Henry in more than 200 years ago, and on the development of this Henry law constants. Later on, another paper that I really have a pleasure to read was published by Professor Hildebrand in PhysRev in 100 years ago. And more recently, I would say, and in 1976, a group of Willem, Batimo, and Wilcock published fantastic papers on low pressure solubility of gas in liquid water, which for me is still a reference papers that I'm really pleased to invite my students and undergraduate or graduate students to read. Of course, SSED group and made a major work on solubility data series, and especially volume 7, and the extension has been published then. And volume 7 is for people dealing with gas solubility, a very important point of information, specifically for oxygen solubility in water, for example. And this paper has been compiled and published in 1981. More recently, the group of Dominique Richon from Paris published a very interesting review papers on carbon dioxide water system, and clearly mentioning formation of hydrates and how this formation could cause a problem within solubility measurements, specifically at low temperature. And they extend the model in order to fit our data within a large temperature and pressure range. And as I mentioned, volume 7 has been extended within the volume 103, and within a large group of very fantastic scientists, including Professor Clever, Bacino, Miyamoto, Jampolsky, and Jung, that they compile series of experimental data for oxygen in water, but also they publish several solubility data for organic liquids, including also ionic liquids, which is, from my point of view, one of the more interesting, I would say, data recommendation papers that I am pleased to share again with my students. More recently, Professor Sanders published a compilation of Henri Low constant for water as a solvent. Again, I mentioned a lot water because water is critical. Water is very important system and very complicated to modelize some more, even if it's very simple molecule. And water system, as I remember from when I started my PhD, my supervisor all the time told me, you must compare your data with gas solubility in water. So it's why I spend a lot of time to try to understand how gas solubility change in water with temperature and pressure. And more recently, and I just want to highlight this point, IUPAC recommendation change for Henri Low constants. And from the continuation of the previous papers from Professor Sanders, with a large of colleagues from SSCD groups, they publish in Pure and Applied Chemistry and provide, I would say, recommendation on notation on Henri Low constants. And from my view, my perspective, I will only discuss on Henri Low, Henri volatility, HV, as reported here, and when measuring the pressure and record the mole fraction, so HVPX. The group of authors also recommend the reader to look at a website to make a conversion. And the first point by reading this paper, which is very important, is if we do not know the composition of your system, you cannot express your Henri Low constants in all of this descriptor, I would say. And that is also a very important point. Solubility is often expressed for low pressure gas solubility in Henri Low constant, sometime in mole fraction, sometime in mass fraction, sometime in mole per liter, and what is the liter meaning, and sometime in mole per kilogram of solvents, which make more sense in molality scale, and so on. And conversion is very important, specifically when you want to do a data treatment and data analysis. Now, I will move to ionic liquidization. Gas solubility in ionic liquids has been published recently in Chemical Review by the group of Lee. And as you can see, the record of this view, 14,000 times, and citation 708, shows that scientists are very interested on gas solubility and specifically in ionic liquid. Of course, ionic liquid are very specific materials because they do not have vapor pressure. So in some all, we cannot find technically ionic liquid in a gas phase, which makes the calculation of the gas solubility much simpler, specifically when we look at isochoric saturation techniques, which is based on the determination of gas solubility thanks to knowledge of the volume, of course, that you calibrate, and then you record the pressure at constant temperature, that you record both. Of course, different techniques based on different methodology can be used. We can cover gravimetric techniques, including microbalance, quartz crystal microbalance weight method. This method are very well known for polymers, and they are now used for non-volatile solvent or liquid, if you wish. Of course, other synthetic method like Wellbore point techniques is used for ionic liquid, and as well as spectroscopic techniques like infrared, specifically when you know that Antonpar developed a CO2 detector that we can use to directly determine the CO2 concentration in your liquid phase. And NMR techniques may be used if you measuring alkane, alcene, for example, it can be used if you have high pressure NMR tube without any problem. And of course, GCMS are quite often used, not for ionic liquid, but mass spectroscopy techniques are now defined as possible tools to determine specifically mixed gases solubility in ionic liquid in particular. And briefly, gravimetric method, gravimetric microbalance is based on gravity forces, buoyancy, of course, and within the equation, what you are measuring what you need to do with this. Of course, you need the gas density. You need the molar volume of, or the volume of ionic liquid, which means you need a density if you are just putting a well-known quantity of ionic liquid into your sample container. And you need also to know if this occurs, the swelling effect, the swelling volume, in order to take into account this into your gas solubility measurements. However, this swelling effect is all time neglected in many papers. And this may not be a big problem for low gas solubility in ionic liquid like oxygen, nitrogen, argon. However, these gases cannot be technically detected by the machine. And another big problem is we cannot work at pressure higher than 20 bar merely. For the quartz crystal microbalance, basically what we are looking at, we are looking at the QCM as an oscillator, and we need a frequency counter. And what we are measuring is a frequency change over the time. And the solubility can be determined thanks to the formal equation where C1 is a calibration constant, which must be set at the beginning of each measurement with an empty cell, with the gas that you want to set. Of course, this requires a very strict preparation of the sample, and because this technique is very sensible to the signal, and you may have a problem with electrical problem, which may cause artifact in your data, I would like to say. And this must be very well controlled with the temperature of the environment and also the voltage applied. As gravimetric microbalance, this technique cannot be used for very low solubility and work for medium pressure. I had a chance to use one, and I'm not very fan of these techniques, but I had a chance to, with a student from China, to use such a system for ionic liquid. And just to tell you, we start with a blank crystal, and we had the gas, and we record over the time applying different pressure. We record the frequencies, and we do the same type of measurement with by putting a sample and measuring CO2. Of course, the C1 constant was also calibrated and verified, and data was verified with a zeolite 13, which is with CO2 solubility, which is known. I will discuss this later on. Of course, a variation of the solubility directly obtained by the difference of mass, which is related to the different frequencies. And this is just an example. And if we look at this example, why I pick up this, because this data set are not very stable at very high pressure, and showing clearly a limitation of techniques. And of course, we repeat this so many times, and we have to put a measurement longer. But we observe a drift, which was, for our perspective, due to the swelling effect on ionic liquids. But this, for example, such a type of data, from my view, if you want to deal with gas solubility, must be reported to really truly evaluate data. Then other techniques like a weight method are based on mass balance at constant pressure. Of course, we have to sampling the liquid and the gas, and and we need very accurate determination of each quantity in a liquid and a gas phase, basically. And again, this techniques is very limited in terms of accuracy for low gas solubility and can be applied only for low and medium pressure. Scientific method like a bubble point is based on the Kayet apparatus. This technique is, from my point of view, very well set, I would say, and is, however, is not suitable for in the presence of cloudy point phenomenon, and accuracy will really depending on the steering, on the volume calibration, and camera resolution. However, within the progress, technological progress, these techniques tend to be more accurate, will be more accurate over the time, I would say. Just to give you a brief overview, I managed to develop a database for ionic liquids, and I'm currently treat completely all I don't know how many data set, 1,200 data set from literature. We're covering different gases from noble gas, from NO, N2O, N2, hydrogen, oxygen, carbon monoxide, alkane, alcene, fluoroalkane, and so on. And basically, we did try to evaluate each single data set and individually first, and then thanks to a statistical analysis and also to try to evaluate data accounting different data sets. And to give you information who is measuring, and basically paper published mainly from chemistry, moving then from chemical engineering. A very small group are really aligned on thermodynamics, which is, from my point of view, a big issue. Only 10% are solely published by thermodynamics groups. And the rest are from physics a bit, material science, energy fuel, polymer science, electrochemistry, and so on. That is also, could also explain later on why we had issues with literature data. Altogether, this database covered more than 39 gases, and I have more than 20,000, but much more because I have untreated system, including the database. So now I'm working on the 2018 to 2022 papers. And just to give you an idea, and this is a C4-MIM PF6, and the cis ionic liquid, a butyl methylimidazolium hexafluorophosphate, is very well known unstable ionic liquid. And by looking at the CO2 data published at 1 bar, I would say, one can see that the deviation is above 5%, below surrounding 5%. 5% deviation for gas solubility is huge, and specifically for CO2. If we analyze the same with oxygen, hydrogen, argon, nitrogen, we could be up to 200% or more within the literature data. This is a big problem. Another problem is the trend of solubility. And here I report different phosphonium-based ionic liquid, whatever the ionic liquid, as a function with the system as a function of pressure here. And here I put the solubility in more ratio because I had the issues to recalculate all in even in on real constants. It was impossible for me, but anyway, and due to the lack of information, I would say. And so I got information of mole of ionic liquid and mole of gas, so I took a ratio, whatever. That is not so important, I would say. What is important here, what we can see is when we increase the alkane chain, the solubility increase from this graph. And this is true for all ionic liquid covered here. However, by looking at the trend of the solubility as a function of the the pressure, one can see that the data doesn't seem very accurate because each line corresponds to one particular data set. More importantly, when we look at the same graph, pressure as a function of argon solubility expressed in mole fraction for the butylmethylimidazolium hexafural phosphate with argon, everybody can really see deviation from the point, and which seems to be related to the difficulty to determine argon solubility in such materials. And just to give you an idea, argon solubility is 2 orders of magnitude less soluble than CO2, and CO2 we have more or less 5% deviation. So in that case, our estimation is the data are accurate within plus or minus 100%. And some of the data are measured by me, so that's not a group. So anyway, maybe come from ionic liquids. And more importantly, the IUPAC ionic liquid, the hexyl methylmidazolium bisulfonylamide, NTF2, has been measured with the same ionic liquid and same purities, and have been measured by 2 groups, and by the Shiflett group and Brennecke groups. Of course, it's 2 different techniques. It's a Cayette, and here is a quartz microbalance. But anyway, one can see from this graph, if we look at the same temperature, it's a blue curve, for example, here from Shiflett group, and the square light white square here from Brennecke, that the differences are very huge. And of course, by looking at literature, if I go back to Battino papers, one cannot expect that such experimental techniques have such large errors. So probably we have other issues, maybe related to sample. However, in this case, it's the same sample. Probably it's a preparation, probably it's calibration, I don't know. But there is a problem somewhere. And because it's impossible that deviation larger than this occurs in this particular system, particularly for SO2. Of course, Shiflett and Brennecke argue, because Shiflett mentioned that there is a chemical reaction, and Brennecke says that it's physisorption only. So anyway, it's a lot of debate, but this debate has been more or less pronounced in IUPAC data series, volume 103, because none of the data set published for ionic liquid could be really used as a recommended data. And just to give you an example, this from the SDS 103 table, and this is 3 papers, and from the Henri Law constants, from the 3 papers at different temperatures, and all Henri Law constant has been normally recalculated for 1 bar. And this is a group from Brennecke. This is from the group from Germany, Cumlan. And this is from my study, I would say, with Margarita Costa Gomez groups. And when we can see, as you can see, the data moved from 23,283 measured by quartz microbalance, and moved to up to 937 measured by volumetric techniques. And of course, the group of Maurer in Germany say, well, there is no change in solubility. However, no extra data has been published so far to argue on oxygen solubility. The same problem was also related for hydrogen. And I mentioned at the beginning of my talk, hydrogen will be critical, will be very important, because people will move to gray or green or purple hydrogen. And we may find a solution to store hydrogen. Of course, there is technical solution already available, but people were thinking at the moment that it may be possible to use ionic liquid for hydrogen storage. But this is probably not possible, but this is another debate. And specifically when you mix ionic liquid with zeolite and so on, forming porous liquid. I will discuss this later on. And this, when we look at a paper published in 2015 comparing data that I published during my PhD with a group of Mora. One can see that the data from this group are very closer to what we measured in 2006. Anyway, hydrogen solubility is quite low, very low in comparison with for example, with CO2 or even with CO. But we must be able to determine this within a great accuracy, because if we are able to measure hydrogen solubility in water, so why we cannot measure it in even ionic liquid, which non-volatile liquid, which normally may have less problem for the calculation anyway. So, of course, looking at the data that I have in the database, and which reflect some of the SDS volume 103 conclusion, no data set could be recommended, even for the IUPAC sample. And deviation close to 10% for CO2 are quite often reported for all ionic liquids that I have. And deviation with statistical analysis of up to 70% for hydrogen. And basically, people develop models, kind of predictive models using data. However, how it's possible to do so without any recommended data set? That's a good question. So probably prior to move to simulation, probably we need to get a real good data. For in the case of ionic liquid, where could come from this problem? Probably purity of ionic liquid, stability of ionic liquid. We discussed during the previous talk about the purity of materials, and water is very water sensitive, but we have also possibility of unreacted species, presence of halide, presence of metals, and this quantity must be defined in order to properly describe the ionic liquid. And we try, of course, as an editor of the journal, we try to force, I would say, authors to add information specifically for ionic liquid, but information are not always available. Of course, these errors could come from experimental method, problem with calibration. We discussed this point. And of course, we can have also problem with non-calibration of the thermometer, thermocouple, and as Earl mentioned. And of course, we may have different sorts of problems which may explain such difference. However, do readers have access to all data which are necessary to further estimate the quality of published data set? And my answer is simply no. And I will try to explain later on why. Now I just want to move to another class of technological solvents. And I will go very quickly. Porous liquid. And I don't know if you know this class of substances, this class of material. And porous liquid has been defined by Stuart James from Queen's University Belfast in 2007. I had a chance to work with Stuart James and to measure solubility in porous liquid. And this very fantastic kind of liquid, very passion. You have the passion to measure this anyway. And there is three types of porous liquid. Type 1, it's a neat liquid, and which contain molecule with rigid intrinsic cavity. Of course, liquid can be has been defined by Stuart James, and we can agree or not that conventional liquid have extrinsic porosity, and type 1 are liquid with intrinsic porosity. So means you need to define a liquid which very particular moieties, allowing to get pores inside. Type 2 porous liquid are porous material dissolved in a cavity, exclude solvent. And this we can sync to calixarene, for example, type of material. Type 3 porous liquid are material dispersed in a cavity exclude solvent. The difference between type 2 and type 3, dissolve, disperse, can be still argued. However, the type 2 and type 3 are less cost effective than the type 1, because type 1 you need a very good organic chemist to help you to design a liquid with rigid moieties, I would say, to allow porosity. Just to give you an overview, porous liquid has been defined originally in 1994 for the gas option with the original work from Robbins. But it's only after 2007 that with the publication of Stuart James that there is a boom. And last year, I would say, a couple of months ago, and a review on CO2 capture has been already published. And just to give you the time frame, and people are really fascinated by this liquid. And porous liquid must be liquid with intrinsic porosity, as we mentioned, and this may lead to enhance the solubility in comparison with the original liquid. However, my question for people is, can we just say that by dissolving or dispersing, I would say, porous material in a liquid that we are forming a single phase system? Technically, only type 1 could be treated as a single phase system, but this is more philosophical. And just to give you an idea of type 1, and been published by Shanghai group very recently, 7 years ago, and they really start with the hollow silicate sphere, and they make a route of synthesis with organosilicon to get their porous liquid sent to polyethylene glycosilan. And then they got a very complicated structure report here with intrinsic porosity. And this occurs to be liquid at temperature approximately close to room temperature according to their DSC. But I invite you to look at the DSC for people that they are very interested within such kind of material, but also interested with DSC measurements. And this, the motivation was to develop gas separation and to develop membrane to separate selectively CO2 and nitrogen. And that the data are reported from their paper. And I moved to the support information to try to get more information regarding how they determine the selectivities. And basically, selectivity was frankly calculated solely from the permeability of the gas, and which, from my point of view, is incorrect. And they report with different media, including starting material, and they show that their porous liquid show very excellent selectivities. Let's move now to other publication for the type 2 of ionic liquid, and just want to highlight the importance. And these two papers dealing with solubility. One paper is from Stuart James in 2015 in Nature Material. Got already 300 citations nearly by. And another paper from a group of Kiao on the type 2 of ionic liquid on again, Nature Communication. And the first papers are really dealing with gas solubility. And the gas solubility has been measured in a type 2 ionic liquid, porous liquid, sorry. And the porous liquid was based on the chronitaire cage mixed with 15 chrome 5-liter solvent, which has been considered as a non-volatile enough to be to form a non-volatile liquid. And then this group measured the gas solubility in this porous liquid mixed with 1 mole of this mesoporous materials plus 12 mole of the 15 chrome 5 ether solvent in order to get methane solubility, and then later on they measure also hydrogen solubility. And the data clearly show that the presence of porous liquid, or the presence of the cage inside the pure 15 chrome 5 boost the solubility. That was the motivation of showing permanent porosity in type 2 porous liquid. Of course, type 3 porous liquid are a class of material which may be simple to be formed in lab, because we can use any material from zeolite, move to MCM group, then to mill, then to HCUS1, for example, type of structure, and to ZIF, zeolite, imidazolite framework, sorry, and this is very well classified, I would say mesoporous material, and which the solid state isotherm are quite very well described in literature, and also very simple to measure by any BT techniques, I would say, until you calibrate of course, your equipment properly. And this, as I mentioned, I was in Belfast and I had the chance to work with this group, and we measure porous liquid for separation of ethane and ethylene. And then the group of Margarita Costa Gomez published also a type 3 porous liquid by mixing ionic liquid and morph, basically. And it was zeolite imidazolate framework as well. And basically, this shows the importance and the emerging of this new class of material, because if you look at the papers, it's Angevante Chemie, and recently another Nature papers has been published a couple of weeks ago, and showing how suspended pores can boost solubility in water, specifically oxygen solubility in water. And this has been published by Margarita Costa Gomez, whom referee papers published in 24th of August against Nature on microporous water with high gas solubility. And these papers took more than 1 year to be published in Nature, just to give you some idea. And of course, to determine this, we may want to move from homemade equipment or to use turnkey equipment available, commercially available. And just want to highlight the techniques that we develop, I would say at Belfast, that I learned from Margarita Costa Gomez lab in Clermont-Ferrand, and then I developed also in Tours, and now developing in Mohammed VI Polytechnic University. And this technique is really based on isocorrect technique, and very, very simple. If you have a porous liquid and you have a porous liquid containing non-volatile solvents, that's very important. And you can simply determine the Henry law constants, or Henry law volatility expressed thanks to the mole fraction and the pressure, as equal to the fugacity of the pure gas over the mole fraction, more or less. And of course, this can be done thanks to a very well set experimental device and techniques, which must be followed as I will explain now. The first step of any gas liquid equilibrium, low pressure, I would say, gas solubility measurements, you need first to trap a well-known quantity of gas in a well-known quantity, in a well-calibrated liquid bulb. And of course, to reach the equilibrium, you need to have a very well, I would say, stabilized temperature within the full set equilibrium set cell, and you need very high accurate manometer. Then when you reach equilibrium, if you have a non-dead volume valve, I would say, you can determine the quantity that you trap in the gas bulb. Then you simply add your non-volatile liquid at the equilibrium cell. Then you can degas if you must do it, you degas it, and then you just close the valve and put the trapped gas in contact with the liquid. By reaching the time, the equilibrium time, which can take 1 week, 2 weeks, depending on the system, when the pressure is stable, depending what sensibility you have in your manometer, you can determine then the solubility. Of course, requested data to measure low pressure solubility data by using such equipment. You need to calibrate the gas bulb as a function of temperature prior building the cell. So you need to first calibrate this part. And to calibrate this part, I remember when I started my PhD, I was using mercury, but mercury is prohibited. So now, no chance we are using water, and probably we may find better idea, because for low volume, we have a large errors. Anyway, we need to calibrate, thanks to PVT measurements and the calibrate gas bulb, the total volume of the cell as a function of temperature and pressure, of course, or the pressure of interest. You need to determine the purity of each fluid, and also to be sure that your non-volatile liquid is dry first, especially for porous material or ionic liquid, and also well vacuumed to avoid any trapped gas, which may be possible in a very viscous solvent. And we must know the density. That's also a big problem, because density must be known in the volumetric techniques. And the density, I would say, as a function of temperature and pressure, and as well as, if possible, if we have very high solubility, and if we expect or suspect chemisorption, we must determine before and after CO2 or gas, I would say, solubility. The thermal stability of testing material must be known, and which somehow could be stupid. But if you are using a porosimeter and you have to dry your sample, the solid sample, and sometimes you dry it under vacuum at 100 or 200 degrees C for 12, 24 hours to be sure that it's dry enough. But sometimes your material decompose under such a condition. So uncertainty in temperature and pressure and composition must be known as well. And as we discussed previously, how we can determine accurately the uncertainty of solubility. And this, from my point of view, must be done with, could be done in different way. Could be done thanks to the calibration, the repeatability from a reference system, and by measuring and several times, I would say, the system. And basically, my recommendation is to at least do your measurements at least 4 or 5 times, even if each solubility data could take sometime 1 week. And we must also take into account calibrations thanks to reference material, like, for example, water, gas solubility in water, as an example. Another problem that I would like to share, because I had the chance to build different techniques and different materials, and I observe a very big problem. And this is purely from experimental. I use from the valve. I use a constant volume valve, and I use a stopcock, I would say, with that you have to count the number of turns. And the piston could be in Teflon, okay? Or could be in glass or whatever. And if you're measuring gas solubility, avoid Teflon. simply avoid Teflon because you may have problem within stability of your measurements. And if you have to move to the glass valve, you must be aware that specifically a piezo grease H, which is very well known for the vacuum, could absorb a large quantity of hydrogen. And I measure the solubility of hydrogen in a piezo because I start to become crazy with data because the measurement were not, the repetition of data were not there, and the calibration took ages and so on with a small decrease of pressure. And I discover that the problem coming from the valve. And the same steering system, what type of bar you use. It's better to use glass one in glass, but the problem in glass, in isochoric technique, if you broken the glass, you have to recalibrate everything. And so on. And how we can cover the fugacity calculation as well. Do we have to include fugacity or not? That's depending on the system, but if we want to be very strict, you must take into account fugacity calculation. In the case of data request for non-volatile liquid like porous liquid, if we assume that porous liquid are non-volatile and ionic liquid, fugacity calculation may be requested. I all time include the fugacity correction, calculating the compressibility of the gas. And for that, I use a collection of Diamond and Smith for different gases and also for gas interaction, I would say water plus CO2, for example, cross-variable coefficient and so on. Just now, I just want to share, sorry, I'm speaking, just an Excel spreadsheet. And I just said that for my undergraduate students with a collection of Diamond and Smith's data, recommended data, and then we regress the data using a solver, using Linus function. It's very easy to calculate the B coefficient at the expected temperature, I would say. Of course, we did that for different gases, and which may be need for the calibration, for example, and for the measurements. Then I set a volume cell. And if we have isochoric techniques, we need, of course, to get first the gas bulb volume, which could be calibrated in different way, but we decide to calibrate separately using water. And of course, we need to take into account that the calibration must be done at different temperature because we have a stopcock, we have a valve, and which may be a different material. And in order to calculate the dilatation coefficient in order to correct the volume change due to the increase of temperature. And the coefficient is here. And here is a glass, it's a expansion coefficient from glass, for example, material. And then we did the same PVT measurements to calibrate the glass cell, thanks to a very well-known volume, and to determine the total volume. Of course, the gas bulb volume must be set according to the gas that you want to measure and according to the quantity of material that you have. If we are talking about ionic liquids, I remember in 2002, to get 1 gram of ionic liquid was very difficult. Now we can probably have a kilogram, no problem. So probably we can set up equipment with a larger setup than that we done in 2002, for example. And now, and this is particularly important, is a ratio between the gas bulb and the total volume, because this will be somehow expressing the pressure drop. And this pressure drop will give you insight on the possibility to detect a variation of pressure caused by the solubility. That is also very critical when you build equipment. As I mentioned, the density of material is requested to determine the volume of liquid, because we are isocorrect techniques, even if some experimental tools are using the first expansion to determine the volume of the occupied by the liquid, but I think it's incorrect. Then we have to take into consideration the number of mole of gas trapped in a gas bulb. And then I did two calculations for this workshop. I hope everybody can see my screen properly, and my Excel file is larger enough for everybody to read. And here, within this calculation, I put a report randomly 25 degrees C. It's not 25,000, it's impossible. And I report a pressure of 1049.5 millibar. It's a French computer, so you have to read the comma as a dot anyway. And then I calculate the total number of gas trapped in the gas bulb. And you can see there's two values here, and there's not much difference. And this was calculated without taking into account the fugacity, the fugacity equal 1 here, and here is taken into account the fugacity correction, and thanks to the second variable equation. And if I give you some example, this small variation, I did not take into account I consider Z compressibility as equal to 1, and I just compare these two set of data from the same equipment, same values, and I have a 0.5% error. Just a number of mole. Crazy. Because the number of mole is very low, it's 10-2. That's the main reason. Of course, the difference, if I look at the absolute difference, if I look at the difference is 10-5, of course. But this, taking into account repetition of error or uncertainty on the measurements, this is maybe one way to count errors within measurements. So it's why I all the time say, you need to report the data if you are not only the pressure at the equilibrium, but also the initial pressure and the volume or the mass of the liquid put, because without this, it's impossible to control. Then we put, this case is ionic liquid, but anyway, we take into account the mass of the ionic liquid, and thanks to the density at the expected temperature, we determine the volume. Then we wait to reach equilibrium.
Johan.
And yes.
Yes, Johan, sorry for the interruption.
We have to finish.
No, 5 minutes more for you to finish, and then
I finish with this, and I promise I will.
Yeah, but then after
I'm sorry.
10 minutes discussion. No, it is quite great. It's very good. No, it's quite great. It's just because we have to fill some other activities within the.
No problem. When I'm speaking, you stop me anytime. Equilibrium pressure. It was okay. We did a measurement. We got an equilibrium pressure at 900, whatever. And again, I calculate with taking into account the cross variable, taking into account, not taking into account. Of course, this means that phi. Okay, so I'm lost now. You confuse myself. Okay, so yeah, so means phi equal to 1. Yeah, of course. And then just to give you some, because this ionic liquid are very high or really low constant, and these small errors are, well, if you did not take into account the correction, if you are considering ideal gas phase, you may have an error which is non-negligible in terms of the Henry low constant, which is quite huge. And this again, this is particularly true for very for system with very high solubility. For system with very low solubility, you can simply, of course, ignore the non-ideality of the gas phase, the fact that Z not equal to 1 anyway. And if I continue, if you permit, continue up, I do have to close this chat probably anyway. And we develop also techniques doing using mass spectrometry, because if we want to measure gas phase, we must do, and honestly, it's one of the techniques which may be the most accurate, and simply that you can adapt and couple with different techniques. And this has been used to measure the absorption of CO2 in presence of different impurity in ionic liquids that we publish recently, I would say. Anyway, and just to give you some, using such a technique, we determine, and I please look at only at the first line, and it's the solubility, propylene, propane solubility in this ionic liquid P6614 NTF2. And this is a single gas solubility. There's two lines, the circle, it's a pure propylene solubility, and the square, gray square, is a pure propane solubility. So it's a single gas solubility. And if you look at the triangle, open triangle, it's with a mixed feed with a mole ratio of 1:1, basically. And one can see from this that the distribution or separation factor cannot be simply obtained thanks to the solubility, the single gas solubility in ionic liquid, just to echo, or in porous liquid, just to echo published papers published there. Anyway, and just very quickly, because time is running out, and we discuss about commercial pieces of equipment for porous liquid, because people are mainly motivated to use solid sorbent and to mix or to dissolve, I would say, to do a type-free porous liquid. They are really motivated to measure solid state isotherm from their solid material first. And then different group modify porosity method in order to get access to the solubility in liquid, and at different temperature, not only nitrogen, I would say, as is display here, for example. And similarly, Cetaram produced recently high precision gas pro techniques that I will have the chance to test, and I start to test this equipment here in order to further validate its accuracy, I would say. And very quickly, because time is running out, and this microporimeter has been used in a Nature paper published, I would say, 3 weeks ago, or something like that. And basically what they recommend is to determine the free volume, and then they, of course, they determine the volume of the money flow, the volume of the solid of the sample pore, and they record the temperature at this particular place. And thanks to expansion, I would say, measurement, they determine the volume of the cell. Of course, the pressure of the gas will depend in this technique to the dose that will add, because you are working with helium, and then we can add micro sampling, I would say, some gas to then check its solubility in normally in solid, but then they move to porous liquid. And basically, porous liquid looks very fantastic if you read this paper, the Nature paper. However, there is some halides which are non-stability of some zeolite imidazolate framework into water, causing the problem with the long-term stability, and also things we are dispersion. Could we say that the dispersion is a stable phase? That is a question that I ask you directly, frankly. And then limitation is to the techniques. How is possible to determine the oxygen solubility, because the group were unable to determine the solubility with the technique, the pure oxygen solubility in water. And of course, then they argue that by increasing by adding the porous material, they boost up, and then the oxygen solubility was below in water was below the detection limit, and but no problem were looked at when measuring CO2, for example. And just brief note on Cetaram equipment. It's again turnkey equipment, and if you do not have any experience, you may have directly the concentration of gas expressed in different way. And but I received such a piece of equipment that I'm currently testing, but with a fully manual mode, because you have to be aware that such a technique, we have a heater which heating only the sample reservoir and not the full cell, and you need to calculate the gradient, temperature gradient which occur over the full cell, even if you have a thermocouple to guide you. Anyway, but you must take that into account. Anyway, this Cetaram just claim that this equipment is more sensitive because it have 3 micromole. The sensibility is limit of detection is 3 micromole of gas, and the cell moving from 1.2 liters to down to 12 milliliter, showing in many cases enough size to measure solubility within the sensibility expected. Of course, this is mainly driven for working from vacuum to 200 bars. And the system test for this that I'm currently investigating is solid material, is a zeolite 13X, and this is data published by a group in US, and I received the sample to test it and validate the data to further estimate. Anyway, to conclude, because the time is over, probably you want to stop this talk now. And of course, there's a large number of gas solubility in ionic liquid and post-liquid. No data set could be recommended, and based on statistical analysis, which done with all data set published up to 2017. And this is an agreement with Solubility Data Series 103 and conclusion. And of course, the uncertainty in composition of gas solubility is not sometimes very well defined. And I do recommend authors to report repeatability of their measurements, and at least a 3-4 experimental setup data set, and totally independent must be reported to really truly evaluate the uncertainty of such measurements. A calibration must be precise, that's very important. And if oxygen or if gas solubility in model system must be used, water must be set as a model system, and which may be a problem for such sometimes for such equipment as discussed with the posimeter with oxygen. And all solubility data must be reported in details, and specifically for isochoric techniques. I try to pursue you with the Excel spreadsheet too, that this is very important. And please to make great attention on each material used to set up your new equipment, specifically Teflon, grease, and so on. That is for me. I would like to thank you again for your attention. And I don't know if there's any question.
So thank you very much, Johan, for this very comprehensive work and very nice talk. Thank you for learn a lot from you. We did not want you to stop. It's just we need also have some time because there are people already in the chat, including a lot of questions. And so I would ask Hala, Vladimir, also Herl, that if they can, because it would be better just to listen them instead of me or you reading the chat. So please, Hala, the floor is open for some discussion. We have about 10 to 15 minutes discussion period. Please be free to talk and just introduce to Johan some of the comments you have done in the chat.
Okay, I believe the first comments were from Vladimir. He was asking about So about this table where you showed 3 different works reporting solubility of oxygen in, I believe, oxygen in ionic liquid, whether they were reported on the same basis, whether the Henry law constants were reported on the same basis.
Yeah, absolutely. Yeah.
So they were. So, and the second question was about, do you think whether it's good to report just Henry law constants or also all the solubility data underlying the determination of the Henry law constant?
Okay, okay, this will depend, you know, and can we say that Henry law constant is enough? No, because if you have a reactive medium, you cannot use Henry law constant anymore, because you know, if you have chemical reaction, so it will depend on the system. So I know people try to split the physical part to the chemical part, but at the end of the day, you're measuring the solubility. And so from my point of view, if you're measuring by using I would say isochoric techniques, because I know very well this technique, you must report first all volume, second all pressure, third the mass of your sample, fourth that you must report the equilibrium time with pressure, because I saw waves with pressure, because when you have water bath, for example, or your air bath, you have variation of temperature with look like a sinusoidal, okay, because this is normal, because you try to fix the temperature, and the amplitude will depend on your accuracy of your mixing, you know, the bath. But you have a second range of oscillation, which may depend on your PID controller and so on. And no one reporting this. You're showing only the first wave, but not the second one. Mm-hmm. And if you look at the signal errors, so anyway, so from an editor of solubility data, I would like to see this data, because this, you can have a drift. And this, I observe the problem with the grease like this. It's crazy. You spend months on measurements, and sometimes you wake up and just say, sorry, fuck off, I say, because I was young. Because I just said, discover that when you put it's a fresh grease. When the measurement you did, sometimes you have a grease going inside. Anyway, for people that they work with such equipment, they know what I'm telling. And when you have a fresh grease, I observe this drift. I just say it's impossible. And then I put a grease in a gas bulb by measuring the solubility. And this comes from this idea, because I observe the first oscillation and the second oscillation have a drift on pressure. And because people claim to measure at 1 Pascal. Do you know to measure at 1 Pascal? When you have a vacuum pump that they cannot have such a 1 Pascal quality vacuum. That's specifically with non-volatile liquid, whatever. Anyway, so we can talk hours and hours on this.
Yeah,
anyway,
I understand from your question that it's so just reporting Henry law constants is not sufficient. Just raw data with all this information would be the best way to report the data. Okay,
yeah, the same with any technique.
Errol has his question.
Well, no, it's not a question. It's a comment. The paper which Johan referred to, where they have gone through and defined the Henry's law constant. The Henry's law constant is actually only defined at infinite dilution. It's the constant in Henry's law.
Absolutely.
So you're not measuring Henry's law constants, no. You're measuring gas solubilities.
Absolutely.
And you have to report those, because the Henry's law constant is an imaginary quantity. It's like the activity coefficient of an ideal 1 mole per liter sodium chloride solution. Yeah. You can't measure it. It doesn't exist.
Yeah, but the people are determining activity coefficient infinite dilution.
Yeah.
You know.
So there's no question of only reporting the Henry's law constant.
No.
Nobody's interested in it by and large. Most people are trying to dissolve a lot of gas. So you need to know what you measured. not what it would be at zero concentration.
Absolutely, yeah. No, I agree. Yeah. And mole fraction or mass fraction definitely better. That's my anyway. And molality could be also interesting, better. Until this is well defined.
Disadvantage, a small disadvantage of this paper in Pure and Applied Chemistry that they mostly give examples on molarity based, not mostly without mass or mole fractions, which would be, I would say, I would give the opposite, give more on mass and molar fraction based rather than molarity, which I would say ill-defined by priori.
I think that reflected the people who wrote it. There was a lot of input from the atmospheric chemistry people, and
absolutely.
That seems to be the way they've reported data, and so it carried through that way.
It's why I mentioned the paper before, just for people to know anyway. Yeah.
And Errol, you had a question in the chat about the effect of viscosity on the uncertainty estimation for the solidity.
I wondered when your measurements, where you had these big differences in measured solubilities in the ionic liquids, whether those differences correlated with viscosities of the ionic liquids.
Yeah, that's a good question, but we cannot find a clear trend because okay, people try to correlate with molar volume, people try to correlate with viscosity and so on, but there is of course if you imagine that the gas bubble can be trapped, okay, that's possible. So means you have a problem with a steering problem, or you did not reach equilibrium material, but at least you're not at the equilibrium. But some ionic liquid are viscosity like 32 centipoise, and you cannot expect to have such bubble trapping problem. Some others have a viscosity much larger, which is okay, we can probably understand. But I just want to remind people that solubility in polymers is possible as well. And people are measuring solubility, gas solubility in polymer with sometimes better accuracy than ionic liquids. I just want to, I don't know where I come from this problem. I don't know if it's a problem of techniques, and I don't know if it's a problem of calibration. I don't know if it's a problem of accuracy of manometer. I don't know if it's a problem of uncertainty with temperature, because people stop to use a triple point cell that no one know how to use that, and nobody use a Western bridge to really measure the temperature. Anyway, we can argue, we can discuss, but I as a scientist collecting data, I want to understand where I come from this problem.